So what we're going to do here is just take a look at a graph of a function and see some of the elements associated with a graph, its derivatives. So I'm going to try to draw I'm going to draw a function. Not going to be pretty, but we'll get the general idea of what we're trying to do. So here, it really doesn't, again, what the function is doesn't really matter. We're just trying to see some of the characteristics. So you can tell from the graph we have, we've got a function, it goes up, it goes down, it's got some intercepts. And what we can do is we can see places where, intervals where the function is increasing, where the function is decreasing. So we can see function values. So we've got increasing, decreasing, increasing, decreasing, increasing, increasing. Okay. Now what we can do is take a look at the first derivative, which is going to be the slope. So here, when values are increasing, first derivative is positive, or slope is positive, slope negative, slope positive, slope negative, slope positive, positive slope. So wherever the function is increasing, so f of x increasing, we have the derivative greater than 0, and when f of x is decreasing, we have the derivative less than 0. Okay. So if we could take this function, find its derivative, any interval, so in this interval here, the derivative would be positive. Here the interval, the derivative would be negative, positive, negative, and then positive. Okay. Then we have these points. So there, right here, right here, here, roughly here, where we're going to have a derivative equal to 0. Okay, so these will be our critical values. So a tangent line here would be have a slope of 0, tangent line here, tangent line here, tangent line here, tangent line here. All those places we're going to have a slope equal to 0. All right. So if we go back to our original graph, what we can do is we can find these critical points, or the places where the tangent is 0, simply by finding the derivative, setting it equal to 0, and then solving for x. So we can find increasing values, derivative greater than 0, derivative less than 0, and we can find where the derivative is equal to 0. The second derivative, so the first derivative is tells us about slope. The second derivative tells us about concavity. So let's say this interval here, up to about there, concave down, to about here, concave up. I don't know, this is roughly concave down, concave up, to about here, concave down, and then at this point, concave up. So where the second derivative is greater than 0, tells us concave up. We would have second derivative less than 0, where the graph is concave down, and where second derivative equals 0 is where we would have inflection points. So this point here, this point here, 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 these will all be places where we have an inflection point, or it changes from concave down to concave up. And we could find these points, these values of x, by setting the second function, by setting the second derivative equal to 0, and again solving for x. And then a little bit about these extreme values, so relative max, relative min, relative max, relative min. Using the first derivative, setting it equal to 0, we can find these points. And then finding the second derivative at that point. So let's take this particular x value right here. What we'll find is the first derivative will equal 0. The second derivative will be less than 0, which will tell us at that point we have this turning point in the graph is concave down, so that's going to be a relative maximum. For this point here, that value of x, the first derivative is going to equal 0, and the second derivative will be positive, which will tell us that at that point the graph is concave up, which means this will be a relative minimum. Same thing here and here. So that's just a little bit about the graph, and how we can use the derivatives to find information that's useful from the graph.